Hello! In this video, we'll design the controller for the single cycle processor. So let's take a look back at our data path. Data path began with the architectural state, the program counter, the register file, and the instruction and data memory. To that, we added an ALU to do the math. We added a sign extender to get the immediate. We added a couple adders for PC plus 4 and PC plus branch offset. And then we added some multiplexers to choose among possible inputs. That gives us the black data path. The data path receives some blue control signals from a controller to tell it what to do. For example, the data path needed write enable signals for the memories. It needed an ALU control signal for the ALU, and it needed multiplexer enables for the sign extender and the various multiplexers. So the job of the controller is based on the instruction we're executing to produce the appropriate control signals. So let's take a look at how to do that. So at the high level, the controller takes in the instruction, and in particular it needs fields the opcode, the funct3 field, and at least bit 5 with a funct7 code to tell whether we're doing the add or subtract. It also needs the 0 flag coming from the ALU to tell us whether a branch should be taken. The output of the controller are the write enable signals, reg-write and mem-write to the two memories, the ALU control signal to tell the ALU what to do, and the multiplexer selects PC source, reg source, ALU source, and immediate source to tell the other parts of the data path what values to select. So let's break this controller down into a lower level into 3 pieces. A main decoder that just looks at the opcode, figures out what type of instruction it is, R type, I type, S type, etc., and provides most of the control signals. An ALU decoder that looks at the type of ALU instruction, the type of R type instruction, and generates the appropriate ALU control. And then PC source logic that looks when we're doing a branch and the result is 0, so values are equal, then tell us that we should do the branch. So we'll design each of these 3 blocks in turn. Let's start with the main decoder. So the main decoder took in the instruction field here, which is op, and it needs to put out all of these different control signals. So for a load word, the op is 3. Load word puts an answer into the register file, so reg-write should be 1. It's an I-type instruction, and we might remember that the immediate source for an I-type was 0, 0. The ALU source, we want to select our second source from the immediate. And looking back here, to choose the second source, source B, from the immediate, ALU source should be 1. A load word does not write to memory, so mem-write should be 0. Load word takes the result from here, so result source should be 1 to take the value that we read from memory. Load word is not a branch instruction, so we'll make branch 0. And now we need an ALU op. ALU op is going to come from the main decoder, and it'll tell the ALU decoder to either add, subtract, or look at the function fields. So for load, we need to add. Let's make ALU op be 0, 0 to indicate an add. Next, let's look at store. So for a store word does not write anything to the register file, it just writes to memory. So reg-write will be 0, but mem-write will be 1. A store word was an S-type instruction, and we might remember that IMM source should be 0, 1 to choose the immediate appropriately for a S-type. ALU source is 1 again, because once again we want to choose source B from the immediate. Result source doesn't matter because we're throwing away the result, we're just writing to memory, not to the register file. This is not a branch, and once again ALU op is 0 to tell us to add the base address to the offset. For an R-type instruction, R-type instructions do write to the register file, so reg-write should be 1. IMM source, well, we're not using the immediate, so it doesn't matter what IMM source is. ALU source, this time we're taking our second source from the register file, so ALU source should be 0 instead. Memwrite is 0 because R-type instructions don't write to the memory. Result source, this time we want to choose our result from ALU result, so result source should be 0. R-type instructions are not a branch, and the ALU op, let's make it 1, 0 to tell the ALU decoder to look at the function field, and we'll design the ALU decoder in more detail shortly. Next, for a branch does not write to the register file, nor to memory, so both write enables are 0. The branch takes a B-type immediate, so IMM source is 1, 0 to select the immediate appropriately. ALU source, the second source should come from the register file, so just like an R-type, ALU source is 0. Result source, we are not using the result, so it doesn't matter what it is. Branch is now 1 because this is a branch instruction, and ALU op, we need to subtract the two registers to compare them, so let's make ALU op 0, 1 to indicate subtract. So now let's go back and review the ALU for a moment. ALU control of 0, 0, 0 meant add, 0, 0, 1 meant subtract, 0, 1, 0 for AND, 0, 1, 1 for OR, and 1, 0, 1 for set less than. And here was our ALU with these different, way we built it was we had an adder, an AND gate, an OR gate. So to do an add, we just take A, we pass B through, so ALU control 0 needed to be 0, and we do A plus B, choose that result 0 because ALU control is 0, 0, 0, and we get out A plus B. For A minus B, ALU control bit 0 is a 1, so this mux chooses not B and puts in a carry of 1 to the adder. So we do A plus B bar plus 1, which remember means subtraction. We get out our answer, ALU control is 0, 0, 1, so we do A minus B. For AND, we're doing A and B, compute that, and when ALU control is 0, 1, 0, we choose the AND. For 0, 1, 1, we choose OR. For set less than, we do a subtract, because least significant bit is 1, so we're doing A plus B bar plus 1 is A minus B. We look at the most significant bit, which is the sign bit, telling us if we're negative. So on set less than, when the result is negative, we want to put that into the least significant bit of the answer and make all the other bits 0. Because if A is less than B, set less than should produce 0, 1, and if A is not less than or equal to B, it should produce 0. So this set less than block takes the sum bit, fills all the other bits with 0, and when ALU control is 1, 0, 1, we choose that answer accordingly. So now let's look at the ALU controllers a little further. it takes the ALU op saying whether to add, subtract, or look at the function bits, and it takes the function bits and it needs to produce that appropriate ALU control signal. So when ALU op is 0, 0, that meant always add. Doesn't matter what the function bits are. We do this for loads and stores, and we want ALU control to be 0, 0, 0. For an ALU op of 0, 1, that is subtract. We use that for branch on equal. Doesn't matter what the function bits are, we produce subtract. When ALU op is 1, 0, that means we need to look at the instruction. So if the funct field was 0, 0, 0, this means we're doing a subtract. 0, 0, 0 means we're either doing an add or subtract. If op5 and the 5th bit of function 7 are both 1, then it's a subtract. That's a little convoluted, but you could figure that out by looking at the encoding of instructions in table B. So for subtract, ALU control should be 0, 1. For any other combination of op and funct, we want to add. The others are more straightforward. When funct3 is 2, we want to do a set less than. When it's 6, we want to do an or. When it's 7, we want to do a set less than. And here are the answers that would come out of ALU control. So ALU control is a block of combinational logic. It has inputs ALU op right here, and funct3 and the op here. And based on those inputs, it computes ALU control, which are these outputs. This column doesn't actually mean any hardware, it's just here to help us understand what instruction we're looking at. And you can use any technique you like for designing combinational logic based on some inputs to design this thing. So let's take a look at an example of the AND instruction. If we're doing an AND, x5 gets x6 and x7. The opcode for AND is 51. That indicates that it's an R-type instruction. So the main decoder puts out the control signals like we talked about. Ridge write is 1. Immediate source doesn't care. ALU source of 0, mem rate of 0, ridge source of 0, branch of 0, and ALU op of 1, 0 from that truth table we built a couple minutes ago. Let's take a look at the operation. The program counter comes out of the value, goes into the instruction memory. We fetch the instruction, which is the AND. The AND, the two sources, x6 and x7, put those addresses into the register file, and we read out the contents of registers x6 and x7. Meanwhile, we send the instruction up to the control unit, and based on that, it produces all of these control signals like we asked for. X6 goes straight to the ALU. X7 goes to the source B multiplexer. Because ALU source is 0, 0, we choose X7 instead of an immediate as the second source. Now the ALU gets an ALU control of 0, 0, 0 from the ALU decoder because ALU op was 1, 0 and the instruction said do an AND. We compute x7 and x6, get our result, and the result multiplexer is receiving result source of 0, telling us choose this result from the ALU. Result comes around and it goes to the register file, and reg write is 1, telling us to write the result of the AND into the register file. Mem write is 0, so we don't write anything to the memory. Branch is 0, so we don't want to do a branch. So we have PC plus 4 comes around, and because branch was 0, PC source will be 0, and we'll choose this PC plus 4 as our next PC.